Hello and welcome back to the second video on getting started with Kubernetes engine. In the last video we have seen this introductory module about in general Google Cloud. Now we'll start this introduction to containers and Kubernetes.
And operate at an unprecedented scale. But what exactly are? Containerization helps development teams move fast, deploy software efficiently, and operate at an unprecedented scale. But what exactly are containers? How do they work? And where does Kubernetes come into play? The goal of this second section of the course was designed to help answer those questions. You'll explore containers, container images, Kubernetes, and Google Kubernetes Engine. You'll also get hands-on practice with Cloud Build. Let's get started.
So yeah, we have a quick theoretical part.
To answer that question, we'll need to first explore how applications are deployed. Not long ago, the common way to deploy an application was on a local computer. To set one up, you needed physical space, power, cooling, and network connectivity. Then you needed to install an operating system, any software dependencies, and finally, the application. When you needed more processing power, redundancy, security, or scalability, you'd add more computers. And it was very common for each computer to have a single purpose, for example, for a database, web server, or content delivery. This practice wasted resources and took a lot of time to deploy, maintain, and scale. Then came virtualization, which is the process of creating a virtual version of a physical resource, such as a server, storage device, or network. Virtualization made it possible to run multiple virtual servers and operating systems on one local computer. The software layer that breaks the dependencies of an operating system on the underlying hardware and allows several virtual machines to share that hardware is called a hypervisor. Kernel-based virtual machine, or KVM, is one well-known hypervisor. Today, you can use virtualization to deploy new servers fairly quickly. With virtualization, it takes less time to deploy new solutions. Fewer resources are wasted, and portability is improved because virtual machines can be imaged and easily moved. However, an application, all its dependencies, and operating system are still bundled together. It's not easy to move a VM from one hypervisor product to another, and every time you start a VM, its operating system takes time to boot up. But running multiple applications within a single VM creates another problem. Applications that share dependencies are not isolated from each other. The resource requirements of one application can starve other applications of the resources they need. Also, a dependency upgrade for one application might cause another to stop working. You can try to solve this problem with rigorous software engineering policies. For example, you can lock down the dependencies so that no application is allowed to make changes. But this can lead to new problems because dependencies need to be upgraded occasionally. You can also add integration tests to ensure applications work as intended. However, dependency problems can cause novel failure modes that are hard to troubleshoot. Plus, it really slows down development if you have to rely on integration tests to confirm the basic integrity of your application environment. The VM-centric way to solve this problem is to run a dedicated virtual machine for each application. Each application maintains its own dependencies, and the kernel is isolated, so one application won't affect the performance of another. The result is that two complete copies of the kernel are running. Scale this to hundreds or thousands of applications, and you see its limitations. A more efficient way to resolve the dependency problem is to implement abstraction at the level of the application and its dependencies. You don't have to virtualize the entire machine, or even the entire operating system, just the user space. The user space is all the code that resides above the kernel, and it includes applications and their dependencies. This is what it means to create containers. Containers are isolated user spaces for running application code. Containers are lightweight because they don't carry a full operating system, can be scheduled or integrated tightly with the underlying system, which is efficient, and can be created and shut down quickly because they just start and stop operating system processes, container, the kernel, and it includes applications and their dependencies. This is what it means to create containers. Containers are isolated user spaces for running application code. Containers are lightweight because they don't carry a full operating system, can be scheduled or integrated tightly with the underlying system, which is efficient, and can be created and shut down quickly because they just start and stop operating system processes and don't boot an entire VM or initialize an operating system for each application. With containers, you can still develop applications in the usual ways on desktops, laptops, and servers. However, the container can execute final code on VMs. The application code is packaged with all the dependencies it needs, and the engine that executes the container is responsible for making them available at runtime. But what makes containers so appealing to developers? First, they're a code-centric way to deliver high-performing, scalable applications. Second, containers provide access to reliable underlying hardware and software. With a Linux kernel base, developers can be confident that code will run successfully, regardless if it's on a local machine or in production. And if incremental changes are made to a container based on a production image, it can be deployed quickly with a single file copy. This speeds up development. And finally, containers make it easier to build applications that use the microservices design pattern, that is, with loosely coupled fine-grained components. This modular design pattern allows the operating system to scale and upgrade components of an application without without affecting the application as a whole. An application and its dependencies are called an image, and a container is simply a running instance of an image. By building software into container images, developers can package an application and its dependencies are called an image, and a container is simply a running instance of an image. By building software into container images, developers can package and ship an application without worrying about the system it will run on. But to build and run container images, you need software. One option is Docker. Although this open source technology can be used to create and run applications in containers, it doesn't offer a way to orchestrate those applications at scale like Kubernetes does. Later in this course, you'll use Google's Cloud Build to create Docker-formatted container images. A container has the power to isolate workloads, and this ability comes from a combination of several Linux technologies. The first is the foundation of the Linux process. Each Linux process has its own virtual memory address space, separate from all others, and Linux processes can be rapidly created and destroyed. An application and its dependencies are called an image, and a container is simply a running instance of an
at a normal
formatted container images. A container has the power to isolate workloads, and this ability comes from a combination of several Linux technologies. The first is the foundation of the Linux process. Each Linux process has its own virtual memory address space, separate from all others, and Linux processes can be rapidly created and destroyed. The next technology is Linux namespaces. Containers use Linux namespaces to control what an application can see, such as process ID numbers, directory trees, IP addresses, etc. It's important to note that Linux namespaces are not the same thing as Kubernetes namespaces, which you'll learn more about later in this course. The third technology is Linux cgroups. Linux cgroups control what an application can use, such as its maximum consumption of CPU time, memory, I/O bandwidth, and other resources. And finally, containers use union file systems to bundle everything needed into a neat package. This requires combining applications and their dependencies into a set of clean, minimal layers. Let's explore how this works. A container image is structured in layers, and the tool used to build the image reads instructions from a file called the container manifest. For Docker-formatted container images, that's called a Docker file. Each instruction in the Docker file specifies a layer inside the container image. Each layer is read-only, but when a container runs from this image, it will also have a writable, ephemeral, topmost layer. Let's explore a simple Docker file. A Docker file contains 4 commands, each of which creates a layer. For the purposes of this training, this Docker file has been a little oversimplified for modern use. The from statement starts by creating a base layer, which is pulled from a public repository. This one happens to be the Ubuntu Linux runtime environment of a specific version. The copy command adds a new layer, which contains some files copied in from your build tool's current directory. The run command builds the application by using the make command, copied in the runtime environment of a specific directory. The run command builds the application, which contains some files copied in from your build tool's current directory. The run command builds the application by using the make command and puts the results of the build into a third layer, a public repository. This one happens to be the Ubuntu Linux runtime environment of a specific version. The copy command adds a new layer, which contains some files copied in from your build tool's current directory. The run command builds the application by using the make command and puts the results of the build into a third layer. And finally, the last layer specifies what command you should run within the container when it's launched. When you write a Docker file, the layers should start with those least likely to change at the top, and the layers most likely to change at the bottom. So I mentioned this Docker file example is oversimplified. Let me explain what I meant. Currently, it's not a best practice to build your application in the same container where you ship and run it. After all, your build tools are at best just clutter in a deployed container, and at worst, they're an additional attack surface. Today, application packaging relies on a multi-stage build process, where one container builds the final executable image, and a separate container receives only what is needed to run the application. When launching a new container from an image, the container runtime adds a new writable layer on top of the underlying layers. This layer is called the container layer. All changes made to the running container, such as writing new files, modifying existing files, and deleting files, are written to this thin, writable container layer. And they're ephemeral, which means that when the container is deleted, the contents of this writable layer are lost forever. The underlying container image remains unchanged. So when it comes to application design, this means that permanent data must be stored somewhere other than a running container image. Because each container has its own writable container layer, and all changes are stored in this layer, multiple containers can share access to the same underlying image, and while still must be stored somewhere other than a running container image. Because each container has its own writable container layer, and all changes are stored in this layer, multiple containers can share access to the same underlying image, and while still maintaining their own data state. This allows container images to get smaller with each layer. For example, a base application image might be 200 megabytes, but the difference to the next point release might only be 200 kilobytes. When building a container, instead of copying the entire image, it creates a layer with just the difference. When running a container, the container runtime pulls down the layers it needs. When updating a container, only the difference needs to be copied. This is much faster than running a new virtual machine. So, how can you get or create containers? It's common to use publicly available open source container images as the base for your own images or for unmodified use. Google maintains artifact registry at pkg.dev, which contains public open source images. It also provides Google Cloud customers with a place to store their own container images and is integrated with Identity and Access Management, IAM. This allows storing container images that are private to your project. Container images are also available in other public repositories, like the Docker Hub registry and GitLab. Google provides a managed service for building containers called Cloud Build. Cloud Build is integrated with Cloud IAM and was designed to retrieve the source code builds from different code repositories, including cloud source repositories or Git-compatible repositories like GitHub and Bitbucket. To generate a build with Cloud Build, you must define a series of steps. For example, you can configure build steps to fetch dependencies, compile source code, run integration tests, or use tools such as Docker, Gradle, and Maven. Each build step in Cloud Build runs in a Docker container. From there, Cloud Build can deliver the newly built images to various execution environments, including Google Kubernetes Engine, App Engine, and Cloud Run functions. Now it's time to gain some hands-on experience with Cloud Build. In the lab titled Working with Cloud Build, you'll use provided code to build a Docker container image and a Docker file. From there, you'll upload the container to the Google Cloud Artifact Registry, which is a private Docker repository to securely store and manage Docker images.
Let's go. So we have this lab here, which looks like a short one. So confirm that needed APIs are enabled. Cloud Build. So we go to APIs and services. Oh shit, Spain, yeah. We go to library and search for Cloud Build. Enable. This app is enabled already. And now we have the artifact. Oh shit, artifact registry API. Try this app is enabled, okay. Task 2, building containers with Dockerfile and Cloud Build. So we go to activate Cloud Shell, create an empty quick start SH file. Okay. Okay, so now we insert this. Okay, so create an empty Docker file from Alpine. What's the, it's Alpine Linux, okay. Following commands in the Docker file. So copy in the root directly quick start sh. Then start quick start. Okay. Create a new Docker repository. Cloud should run the following command to make it. Oh, sure. Okay. Create a new Docker repository named Quick Start Docker repo in the local use central one. Okay. So, Cloud Artifacts repositories create Quick Start Docker repo repository format Docker. Okay. And other options like the location and description. Then in Cloud should run the following command to build the Docker container image in Cloud Build. So first of all, we create in Google Cloud Artifacts the repository, and then we go to Google Cloud Builds and submit a build with the tag. And using the Quick Start Docker repo name, which we specified here, we basically create this tag here. In Google Cloud Console, in the search bar, search for artifact registry. Okay. Click the repository. Okay. Okay, now building containers with a cloud build configuration file and cloud build. So cloud build also supports custom build configuration files. In this task, you will incorporate an existing Docker container using a custom YAML formatted build file with cloud build. So we first create a file with this content, specifying the steps of the build. So the build will have this name and argument, your region here, Docker pp. Run the below command to set our region variable and insert the value into the YAML file. What is this set command? What is set command in Linux? It's a powerful tool used for basic text transformation manipulation. Okay. So this will replace the first occurrence of all text with new text in each line of the file name. Okay. And it's stream editor. Nice. Wow. In Cloud shall execute the following command to view the contents of Cloud Build YAML. Okay, so now we should see. Perfect. So you can write things like regional locations in files using variables, environment variables from the console. Wow. This file instructs Cloud Build to use Docker to build an image using the Docker file specification in the current local directory tag. Tag it with gr is a substitution variable automatically populated with Cloud Build with the project. Okay. and then push the image into artifact registry. So now we do build submit ---- config okay. So using a YAML file we can also build with some deeper specifications. If we go to the artifact registry, got it. In quick start Docker repo, 2 versions are available of the image. That's not true. Oh, okay, I see. Check my progress. Okay, in the Google Cloud Console, search for Cloud Build, history, click on ID, blah blah blah. Now in the Cloud Shell, okay, replace the existing with the following. So yeah, there's a way to... Oh shit, what's this? Okay, this is if then else. Okay, if minus z, I don't know how to read this condition. Minus z, that should be an argument, is 1, actual word of the time is date, okay, whatever. Yes. Oh. Now we create another cloud build YAML file. We put other steps. Name GCR GCR.io, args, name, images, blah blah blah. Okay, yeah. Okay, now with the stream editor, we substitute in this second cloud build your region here with the region we have memorized in the environment variables. We can check if the stream editor worked. It looks like it worked. In addition to its previous action, this build configuration file runs the quick start image it has created. In this task, the quick start sh script has been modified so that it simulates a test failure when the argument file is passed to it. Now we can submit the build with the configuration 2. It should return an error if I did not understand. Yeah. Build, okay, step, blah blah blah, error, okay. So this is what, yeah, okay, you have a build, an error, confirm that your command shall knows that the build failed, HR. Okay, so we'll end this lab. Let's go. Now a quick theory about Kubernetes, and then we go with the rest of it.
Organization has implemented containers, and because containers are so lean, your co-workers are creating them in numbers that exceed the counts of virtual machines you used to have. Let's also say that the applications that run in the containers need to communicate over the network, but you don't have a network fabric that lets containers find each other. Kubernetes can help. So what is Kubernetes? Kubernetes is an open source platform for managing containerized workloads and services. It makes it easy to orchestrate many containers on many hosts, scale them as microservices, and easily deploy rollouts and rollbacks. At the highest level, Kubernetes is a set of APIs that you can use to deploy containers on a set of nodes called a cluster. The system is divided into a set of primary components that run as the control plane and a set of nodes that run containers. In Kubernetes, a node represents a computing instance, like a machine. Note that this is different to a node on Google Cloud, which is a virtual machine that runs in computing you. You can describe a set of applications and how they should interact with each other, and Kubernetes determines how to make that happen. Kubernetes supports declarative configurations. When you administer your infrastructure declaratively, you describe the desired state you want to achieve instead of issuing a series of commands to achieve that desired state. Kubernetes' job is to make the deployed system conform to your desired state and to keep it there in spite of failures. Declarative configuration saves you work. Because the system's desired state is always documented, it also reduces the risk of error. Kubernetes also allows imperative configuration, in which you issue commands to change the system state. One of the primary strengths of Kubernetes is its ability to automatically keep a system in a state that you declare. Therefore, experienced Kubernetes administrators use imperative configuration only for quick temporary fixes and as a tool when building a declarative configuration. Now that you have a better understanding of what Kubernetes is, let's explore some of its features. Kubernetes supports different workload types. It supports stateless applications such as Nginx or Apache web servers, and stateful applications where user and session data can be stored persistently. It also supports batch jobs and daemon tasks. Kubernetes can automatically scale containerized applications in and out based on resource utilization. Kubernetes allows users to specify resource request levels and resource limits for workloads. Resource controls help Kubernetes improve the overall workload performance within a cluster. Kubernetes is extensible for a rich ecosystem of plugins and add-ons. For example, Kubernetes custom resource definitions let developers define new types of resources that can be created, managed, and used in Kubernetes. And finally, because it's open source, Kubernetes is portable and can be deployed anywhere, whether on-premises or on another cloud service provider. This means that Kubernetes workloads can be moved freely without vendor lock-in. What if you started using Kubernetes, but the infrastructure is too much to maintain? This is where Google Kubernetes Engine comes in. Google Kubernetes Engine is a managed Kubernetes service hosted on Google's infrastructure. It's designed to help deploy, manage, and scale Kubernetes environments for containerized applications. GKE is fully managed, which means the underlying resources don't have to be provisioned, and a container-optimized operating system is used to run workloads. Google maintains these operating systems, which are optimized to scale quickly with a minimal resource footprint. Google Kubernetes Engine offers a mode of operation called GKE Autopilot, which is designed to manage your cluster configuration, like nodes, scaling, security, and other pre-configured settings. When you use GKE, you start by directing the service to create and set up a Kubernetes system for you. This system is called a cluster. The GKE Auto Upgrade feature ensures that clusters are always upgraded with the latest stable version of Kubernetes. The virtual machines that host containers in a GKE cluster are called nodes. GKE has a node auto repair feature that was designed to repair unhealthy nodes. It performs periodic health checks on each node of the cluster, and nodes determined to be unhealthy are drained and recreated. Just like Kubernetes supports scaling workloads, GKE supports scaling the cluster itself. GKE is integrated with several services. Cloud Build uses private container images securely stored in Artifact Registry to automate the deployment. IAM helps control access by using accounts and role permissions. Google Cloud Observability provides an understanding into how an application is performing. And Virtual Private Clouds, which provide a network infrastructure, including load balancers and ingress access for your cluster. And finally, the Google Cloud Console provides insights into GKE clusters and their resources, and a way to view, inspect, and delete resources in those clusters. Although open source Kubernetes provides a dashboard, it takes a lot of work to set it up securely. With the Google Cloud Console, however, there's a more powerful dashboard for your GKE clusters and workloads that you don't have to manage.
What is the name of the computers in a Google Kubernetes Engine cluster that run workloads? What is significant about the topmost layer in a container? An application running in a container can only modify the topmost layer. Reading from or writing the topmost layer requires special software libraries. When using Kubernetes, you must describe the desired state you want, and Kubernetes' job is to make the deploy system conform to that desired state and keep it despite failures. What is the name of this management approach? Declarative. Okay, next. So we finished this module, which was about was an introduction to containers and Kubernetes. Now we have the part about Kubernetes architecture. I think that I will do a quick pause. Therefore, I will stop this video, and in the next one I will continue with Kubernetes architecture. Thank you very much.